Good evening, everybody. Um, Already about 3 minutes past 7:30, so I'll go ahead and start sharing screen so we can get started so that we can get through the majority of today's content. Okay. And everyone see my screen okay? Okay, perfect. I see one thumbs up, so I'll assume all of you can. But for today's lesson, what we're going to be talking about is we're kind of going to be building over what we talked about last time. So in our last session, we went over functional groups and common ones that are in organic chemistry, the really most important ones. And this time around, what we're going to be going over is we're going to first start off by reviewing the nomenclature that we went over last time. We're going to do a quick review on that. Specifically, I'm going to have you guys interact with me largely, and I'm going to ask you specifically, like, what do you remember about what from the last session? And then we'll move into some common experimental techniques that you can expect to see on your exam and just try and go over them as in depth as possible, but not too in depth beyond the scope of the MCAT. Okay, so again, just reiterating, so for today, in terms of like learning objectives and topics that we're going to cover, first we're going to start by reviewing nomenclature of common functional groups. Then we're going to go over organic separatory techniques, so specifically ones that you might have seen in organic chemistry class. There's also going to be some that you might have seen in your organic chemistry lab, for those of you who took organic chemistry lab. There's going to be some familiar ones. And then we'll talk about some spectroscopy and spectrometry, which is, I know, is talked about a lot in Organic Chemistry 1. So that should feel familiar or ring a bell for anyone who's taken those classes already. Okay, so starting off with a nomenclature review. So I'll start off by turning the floor to you guys and asking you what you remember about everything that we went over. So alcohols, carboxylic acids, ketones, aldehydes, nitrogenous and sulfuric compounds. Starting off with alcohols, in terms of nomenclature, what are some common nomenclatures for regular alcohols in terms of like prefixes and suffixes? What do we see for alcohols? The suffix is all, exactly, that's perfect. And what happens when I'll actually ask another question. How do we determine whether or not we're going to take the suffix of a functional group? Priority, exactly. Priority is going to be one of the most important things when it comes to nomenclature, because if you neglect priority, your name will end up being incorrect. So, assuming that we don't have, alcohols are not the priority substituent, what would be the nomenclature term for any alcohol that we see? Hydroxy, exactly. The prefix hydroxy is going to be common for that. Okay, that's perfect. Okay, so what happens when we have cyclic alcohols? What are those called? Especially, give me the name of the aromatic alcohol we talked about. Exactly, phenols. Exactly. So what's going to be different about phenols and regular alcohols? Phenols are more acidic, specifically because of what? What's going to increase their acidity?
Aromaticity.
Exactly, aromaticity. So whenever we're considering acidity or basicity, conjugation, all of that. So whenever we're considering those things, what we're always looking at is the stability of the conjugate base. So the more stable our conjugate base is, the more willing we are going to be to donate that proton. The more willing we will be to try and get to that state of our conjugate base because that's going to be our more stable form. So we'll be more reactive, we'll be more acidic. Okay, that's perfect. Okay, in terms of carboxylic acids, that's everything most important for alcohols. So carboxylic acids, what is going to be the suffix for carboxylic acids? Oic acid. And at what point do we take the name of the carboxylic acid versus something else? Always, exactly. Because carboxylic acids are going to be the highest priority substituent. So if you see a carboxylic acid, it will almost always end in oic acid or carboxylic acid if we're dealing with a cyclic compound. Okay, can anyone let me know some of the carboxylic acid derivatives that we went over? So ketones and aldehydes will be separate from carboxylic acids, but amides, that's perfect. Esters, acid anhydrides. There will also be acyl halides. All of those you should definitely make sure that you're familiar with, at least to the point where it's like you can recognize them on the MCAT, or if you see them in a name that you recognize the name, it's unlikely that you're going to have to do a significant amount of naming carboxylic acid derivatives, but just knowing how to recognize them, being familiar with them is going to be the most important part. Okay, ketones and aldehydes. For ketones, what's going to be the suffix? Oh, exactly. It'll exactly be on. An example is acetone. That's the common suffix you'll see for ketones. What about aldehydes? Al, exactly. Al for aldehydes. And what's going to be the shared prefix that they'll use if they are not going to be the of priority? Oxo, exactly. And with that, since they're shared, how will you be able to tell whether or not you're dealing with a ketone or an aldehyde? Location, exactly. So remember, whenever you're naming anything, whenever you're dealing with nomenclature, especially if you have multiple substituents, you'll preface where that functional group is located. So it'll be like a 1-oxo, then you're most likely dealing with an aldehyde. If you have a 5-oxo and then you have a 8-carbon molecule, then you know, okay, that's mostly going to be a ketone. That's perfect. And that's everything I want to say about that. With nitrogenous and sulfuric compounds, what are some common nitrogenous compounds? Some common ones. I know we didn't get to that portion, so if you guys are familiar on that one, that's okay. Yes, that is correct. Purines, pyrimidines, indoles, pyrols, those are common nitrogenous compounds, especially Indols are big ones that you should make sure you know for the MCAT. Generally for nitrogenous compounds, it'll be easy to recognize them because a lot of times they'll have an AM, like amino, or AMI tends to be in the name for things dealing with nitrogen. So like amino acids, those have an amino group in them. Your amino groups are very important. You'll also have ones that interact with carbon that have different names. I would say all of those. Some are more or lower yield than others. So long as you can identify an amide and you know what an amino group looks like, you'll be largely okay for the MCAT. Sulfuric compounds, what's a phrase that suggests that there's a sulfur group present or a prefix that suggests there's a sulfur group present? It begins with a T. Second letter is H. Um, so close to thiols, thio. So every time you see thio, the immediate thing that you should be thinking of is sulfur. So you have thiols, you have thioethers, thioesters. All of those are going to suggest, oh, I most likely have a sulfur group present. Sulfadils are also ones that are easy to recognize that they have a sulfur group in there. Okay, and there's also going to be an amino acid that contains a sulfur group, which, well, there's two amino acids that contain sulfur groups. Which ones are those? And what's special about them? Exactly. Cysteine and methionine. Cysteine will form double bonds, which is extremely important in terms of protein structure, especially tertiary and quaternary structure. So interactions between R groups. A lot of times you'll see that is driven by disulfide bonds, or that the disulfide bonds are playing a role in it. However, always remember when it comes to protein structure and protein folding, the most important effect is going to be your hydrophobic effect. But cysteine does play a role in that. Methionine, that one also has a sulfur group. It specifically has a thioether group. And cysteine is going to have a thiol group. What's special about methionine in terms of biological function? It's a start codon, exactly. So methionine, AUG, start codon. Perfect. Okay. How do we feel about that? Do we want to do a deeper dive into nomenclature? Are we good on that? Are we ready to move on to experimental techniques? So getting into separatory techniques. Thumbs up or a 6 in the chat for a yes. Thumbs down or a 9 in the chat for no, go back and explain something. Okay. Okay, So getting into organic chemistry separatory techniques, starting off with distillations. We'll also make this as interactive as possible. Also feel free to unmute yourself and say something. You don't have to just say it in the chat. And let me also make sure. Okay, there is no Q&A. Okay. So distillations are useful for separating liquids that have different boiling points specifically. Can anyone tell me what's the difference between when we're going to use simple versus fractional distillation?
Fractional is for like smaller boiling point differences.
Exactly. Fractional distillation is going to be for when you have two liquids with closer or very similar um boiling points. Specifically, the rule of thumb tends to be 25 degrees Celsius. So if it's greater than 25 degrees Celsius, then their difference is greater than 25 degrees Celsius. Then we'll go for simple distillation. If it's less than a difference of 25 degrees Celsius, then you'll go for fractional distillation. That's because fractional distillation is going to add a fractionating column, which will further separate them. Okay. Vacuum distillations. When do we use a vacuum distillation? When does that become useful? Greater than 150. Actually, can I rotate on this? Simple, greater than 25 degrees Celsius. Fractional, less than 25 degrees Celsius. And Ryan, you are exactly correct. Vacuum will be for super high. Boiling points greater than 150 degrees Celsius is also a good rule of thumb for when it's useful. So summarize for when it's useful, it's going to be separating liquids with different boiling points. Okay, does that make sense? Good to move on. I don't see a thumbs down. Okay. In addition to distillations for separating liquids, we also have extractions, which are going to operate on the basis of solubility. So they're going to attempt, or their objective is going to be separating compounds based off of their solubility. So oftentimes you'll have an organic and an aqueous phase separation. What types of compounds or liquids do we expect to see in organic versus aqueous phases, in the organic versus aqueous phase? Okay. So when it comes to the organic versus aqueous phase, a lot of times what you'll see in the organic phase is going to be your nonpolar or uncharged molecules. In your aqueous phase, what you'll see is your polar charged denser molecules. And another large thing that tends to come into play when you're dealing with extractions is going to be pH gradients. So whenever you're dealing with like acid-base chemistry, or if you know that you're trying to separate things that have very different pKa's, what you can do is you can adjust the pH of the solution. That way you have one charged molecule and one uncharged molecule based off of its pKa's and isoelectric points. If you can get the molecule to its isoelectric point where, or a state of where it's no longer charged or uncharged, that's where you will that's how you can then further separate them, because you can essentially make your own non-polar molecule, or you can change the molecule to a non-polar state and then separate out that acid or that base of interest. Okay, moving on. Chromatography. Okay, so there's several different types of chromatography. The main idea and the main takeaway, it's really just going to be that your solutes are going to be separated based off of polarity. So now, in terms of the types of separations we've seen boiling points, we've seen solubility, and now with chromatography principles, we're going to see polarity. So, mobile and stationary phase. Can anyone tell me what they know about the mobile and stationary phases, or do we know anything about mobile and stationary phases?
Isn't the mobile phase like dependent on like the gel use? So usually it's like silica, so it's polar, and the
Exactly. Keep going. You're exactly correct.
okay, and the other one's usually like non-polar, and then how you can like measure like how far it moves up, and that's like RF or something like that, from what I remember.
Exactly. Well, the RF is is pretty characteristic of thin layer chromatography, which we'll talk about, and also so is that silica gel, but it's very common in chromatography generally. And all of those are high yield things and testable. The RF is testable, and silica gel is also testable. The biggest things that Dhruva said are going to be that oftentimes we're going to have a non-polar mobile phase and a polar mobile phase and a non-polar stationary phase. And essentially the way that what most chromatography is going to do is it's going to act and it will show us the movement of the molecule, and that mobile phase is going to do as the name suggests, it's going to pull the solute along the stationary phase. And the more that it moves, more likely the more polar it is because it moved along with our polar mobile phase. And you can also reverse this. In reverse phase chromatography, you have nonpolar stationary phase, polar mobile phase. In typical chromatography, you have a polar stationary phase, a nonpolar mobile phase. Okay. So just remember, mobile will move solute along. largely different polarities. Of molecules. Okay. Okay. So types of chromatography. So as we kind of just said, TLC or thin layer chromatography is going to be one of the most discussed and you're one that you're most likely to encounter type of chromatography. So it will be placed on the bottom of a polar plate, such as silica gel. And the solvent phase will travel up the plate. So the nonpolar solutes will have a greater affinity for the mobile phase and they'll travel higher up the plate. Example is this yellow dot is likely the most non-polar. And polar solutes don't move as much. Oh, when is reverse chromatography used? So it'll be dependent on what kind of separation you're trying to get. So if you know that what you're trying to separate out is a bunch of, if you know that you have a whole bunch of, let's say you have 5 nonpolar molecules and 1 polar molecule of interest, you can very easily just use standard standard chromatography to separate out your nonpolar molecules from your polar molecule. But if you have the reverse case where you have a bunch of polar molecules and you want to separate out this nonpolar solvent, that's when you would use reverse chromatography. So it's all going to be dependent on what you want to move away from one another. That's how you should approach it. Is that okay? Okay. Column chromatography is going to use a stationary phase that's packed into a column, and the mobile phase is going to travel the sample down the column. It's very similar to, or it's largely going to be affinity chromatography. So another type of column chromatography, you'll have size exclusion chromatography, you have cation and anion exchange chromatography. Those are common types of column chromatography. And the way that they're going to work is you will you'll measure like the elution speed, or you'll look at the way that things will elute. So in like cation versus anion exchange chromatography, actually, I'll turn that question back on to you guys. In cation exchange chromatography, are we getting cations, or will our cations be trapped inside the column, or will they be what's eluted? Eluted. Yes, cation exchange traps cations. Exactly. That's exactly, actually, no, it's cation exchange will elute them. So cation exchanges will have negative charges. Will trap cations. No, Ryan, you're correct. Cation exchange chromatography is going to try to capture the cations. So they're going to be stuck inside of that column. So when you think about cation exchange chromatography, what's going to be inside of the column is going to be negatively charged, kind of negatively charged balls that will grab on to your cations and keep them inside of the column. What will elute will be anything that's not positively charged. So negatively charged and uncharged or neutral compounds will elute in cation exchange chromatography. Same principle exists for anion exchange chromatography. For size exclusion chromatography, that way they kind of choose a weight or a size range, and only those size molecules will go inside of the beads, go into the size specific beads. And that's how that one will work. Okay, gas chromatography is going to use a gaseous mobile phase and then a liquid stationary phase. It's only going to work for compounds that are able to be vaporized at reasonable temperatures. And then lastly, another important one, I had actually exactly one question on HPLC on my actual MCAT exam. And high performance liquid chromatography is going to use a liquid mobile phase moving through a solid stationary phase, and it's done at high pressures. That's going to be the biggest thing about that. So the stationary phase for HPLC is typically polar and non-polar for reverse phase HPLC. And that one is testable. Recrystallization and filtration. Okay, there's, for everyone who's taken Orgo or Gen Chem lab, we end up doing recrystallization experiments. Why do we do them? Purity, exactly. To get a more pure compound. So recrystallization is going to purify our compound. Does anyone know or remember why recrystallization is able to help us get to a more pure compound? Okay, that's fine. Essentially, the process, the general principle, or what you need to know. Okay, yes, exactly that. Reheating and slowly cooling down the sample helps to eliminate the chance of impurities and also helps to get rid of impurities. And you can repeat the process to further purify your sample. That's exactly correct, Ethan. And filtration is going to work the exact way that you see in this picture. It's going to function to separate a solid from a liquid. As the name suggests, sometimes you use a filter paper, sometimes there's vacuum filtration. And okay. This is going to be helpful when you're dealing with different types of states of a molecule. If you know that you've done a series of experiments or you've gotten to the cooling point, they have different melting and cooling points. You can separate a liquid from a solid or from the precipitates, and you can then perform recrystallization experiments to purify your solid precipitates. Okay. Okay. Some practice questions. I'll give you guys about a minute to answer this. I still haven't figured out how to create polls for this. Um, yeah, please just you can just send me your answer. Okay. Been about a minute and a half, so we can start answering this. For this, I see in terms of messages I got, the majority I got was B, which isn't necessarily completely wrong. Size exclusion chromatography is a way that we could separate ethyl and butanone, but there will be a better approach. So the reason why we wouldn't want to use size exclusion chromatography for this is that we typically want to separate larger molecules with this. So size exclusion chromatography is also typically used for macromolecules like proteins. You would also want a greater size difference. For it to be the most effective. So outside of that, what's another way that we could approach separating the two molecules? Knowing that we can't do B, I can just go over the questions. So simple distillation, as we talked about, this is for boiling points greater than 25 degrees Celsius of difference. And if we look at these, that's not a 25 degrees Celsius difference. So we can't use that. C, that's going to be boiling points less than 25 degrees Celsius. Well, we are less than 25 degrees Celsius. So that one I would put a question mark. And extraction With extraction, these polarities are largely similar, meaning that we'd be equally likely to find them in the aqueous phase. So their solubilities aren't different enough for us to try and use in extraction. So by process of elimination, C would be the best answer. Does that make sense to everyone? Thumbs up, yes. Thumbs down, no. Thumbs up, ready for another question? Okay, perfect. Okay, next question. Give this another 2 minutes. We'll start going over it at 8:16. Okay. So for this, I did get a few answers, and A was correct. Can someone reiterate to me what the stationary and mobile phases in thin layer chromatography? Does anyone remember? Okay. So in thin layer, yes, the stationary phase is polar. Specifically, it's going to be that silica gel. Your mobile phase is going to be a non-polar solvent. Common non-polar solvent is toluene. That's just a common one generally. And for RF, Can anyone tell me how we calculate that? Exactly. Distance traveled over distance to solvent front. Meaning that the one with our highest RF value is going to be the one that's going to move the furthest. And as we remember, what we're doing is we're playing on polarities. Comes to chromatography, that's going to be all about polarities. So your molecule that's going to be the most similar to your mobile phase is what's going to move the furthest. So in order, what's going to be the most non-polar to the most polar molecule you have? Based off of these. Most polar, most non-polar. So this, we can see they may even made it easy for us. This has 3 hydroxyl groups. This has 2 hydroxyl groups. And this has 1 hydroxyl group. So in order of polarity, I'd rank this as the most polar, this in the middle, and this as the least. And therefore, if this is our least polar molecule, we're going to expect for that to be the molecule that will have the lowest RF value. So really we can automatically rule out anything that doesn't have that doesn't start off with an RF of A. Then we just have to determine between B and C next, or A and B next. And we know that B is going to be our next most polar molecule. So A is correct. Does that make sense? Are you ready to move on to the next question? Okay. Give this one another few minutes. We can start going it over it at 8:23 again. Just PM me your answer. Okay. It's 8:23, so we'll start going over it. Majority of the answers I got were A, and that's absolutely correct. So grass chromatography. Very similar to another one of the experiments we talked about, is going to separate based off on boiling points. What was the other thing we talked about that separates based on boiling points? It's another type of organic chemistry. Distillation, exactly. So simple and fractional distillation also separate based off boiling points. Another thing I did not add was that distillations are best when they're done repetitively. So if you do a distillation and then another one and then another one and then another one, that will give you greater separation. So they are additive in terms of their effect. Gas chromatography, very fortunately, you can just do it once because of the fact that we're going to have this retention time in response. Essentially, we're going to see how long it takes for the solution to boil out, meaning that the lower the boiling point, the lower the retention time. So the faster it'll boil out, the lower it was retained. So since C says compound 1 has the lowest retention time and thus the lowest boiling point, we can rule that out because that's true. And I actually got ahead of myself. In our question stem, we have a word that is the absolute most important word whenever you see it. What is that word? Cannot. Exactly. Anytime you ever see the word cannot or not, immediately pay attention to it, because that means you're going to be trying to reverse your way of thinking. Instead of choosing the right answer, you're going to be choosing the wrong answer. The answer that is physically the opposite of whatever that question stem is saying. D, compound 1 could have the lowest molecular weight. This is also true. As molecules get bigger, their boiling points also get bigger. Compound 3 requires greater energy input in order for its vapor pressure to reach atmospheric pressure. That is also true because that is the definition of boiling point, which is when the compound's vapor pressure is equal to atmospheric pressure. Okay. Last practice question before, well, we don't have time, but last question before I guess we close out, and then I can post the rest, or we can talk about briefly IR spectroscopy, maybe. Okay. Give you guys 2 minutes on this one. So 8:28, we can go over it. Okay, for 3 more seconds. 3, 2, 1. Okay. So Majority answer was D, and that is absolutely correct. So they're saying, they're asking us which is going to remain in our organic layer. As we said before when we were talking about extractions, your organic phase is going to be your non-polar or uncharged molecule. And what happens to acids in the presence of bases? What do they do? They will either exchange electrons or exchange protons or exchange hydronium and hydroxide ions, keeping in mind your Lewis versus acid versus your Lewis versus Bronsted-Lowry versus Arrhenius acid-base chemistry. Keep all of that together. But in the case of benzoic acid, and sodium bicarbonate, which is a base. What's going to happen is benzene will be deprotonated. That hydrogen will go to sodium bicarbonate. It will end up with COO minus and benzene instead. And now that it's charged, it will then move into our aqueous phase. And because of that, we know that it won't be an organic phase. And we can then rule out A, because since it's been deprotonated, it's actually going to be an organic phase. B, aniline. NH2 has a more, amines have a more basic pKa. So we know that it's not going to be the one. It has not been protonated, will not be needed to add an acid. Benzoic acid, because it maintains a neutral charge, it does not. So we can rule that one out. Either by process of elimination or just recognizing that the base is going to act on our acid, benzoic acid, we end up with D. Okay, so we are at time. There's an open content session for us to go over spectroscopy and spectrometry. But what I do want to switch over to before we close out is going to be the very last slide I had, which is, what do you actually need to know for the MCAT in terms of everything that we would have gone over? And it would be, you want to know your common IR functional group peaks. Those ones are testable. They do come up. I had actually only one question on it, but it's one of those low-hanging fruit things where it's like, if you just commit it to memory, then it's good. You want to be able to identify equivalent hydrogens, especially in terms of NMR, and knowing whether or not splitting is going to occur. You want to be able to read NMR spectroscopy. If they give you an NMR spectroscopy plot in a passage, you want to be able, like in a chem phys passage, you want to be able to kind of identify what molecule is likely going to be there, or what would happen in terms of shielding and de-shielding. For mass spectrometry, you want to know what the peak height is going to indicate, and also what that MZ ratio is going to mean. You also want to be able to identify characteristic peaks. Biggest thing is always going to be identify characteristic peaks. You want to know how mass spectra are obtained and how they tend to cross over with magnetism. And then some relevant equations are going to be the force of magnetism, and then also just the movement of circular movement. So centripetal acceleration, how that also can translate into a particle in a magnetic field. So knowing how all of those tie into one another. And that's it. I will post these slides on Canvas that will also have all of my notes for like information at the bottom of them. So if there's anything on there that doesn't feel understood, just you can also re-reference the notes and it'll be as if I'm talking to you. So that should be perfect. Okay. Any last minute questions, comments, concerns, requests? How do we feel about, at the very least, organic separatory techniques? Thumbs up for good or better. Thumbs down for I'm going to need to do a lot more practice still. Or you made it worse. Okay. I'm glad. I'm seeing a lot of thumbs up. Okay. Thank you guys for coming.